Hello, and welcome to a video lecture for 501 associated with torsional stress. As you recall from our last lecture, we realized that the partial differential equation for torsion, as shown here, where phi is the stress function, g is the modulus of rigidity, and theta is the angle of twist, has the exact same form as the partial differential equation for a soap film or a membrane that has been stretched over the cross section of the beam or shaft. In the soap film equation, Z is the height of the bubble or the soap film. X and Y are simply the locations in the cross section. P is the pressure, the lateral pressure pushing on the soap film, and S is the initial tension in the soap film. Then we can note that Z is equal to C phi, where again Z is the height of the bubble, phi is the stress function, and C is the constant of proportionality. Rearranging, we can see that P over S is then equal to C times 2G theta. And we can also note these relationships down here. The main takeaway from this is to be able to look at a soap film and realize where the stress is the largest, and that's where the slope of the soap film is the largest. So the slope of the soap film bubble is proportional to the stress. And the area or the volume underneath the soap film is related or proportional to the torque in the system. It's important to be able to visualize these structures and visualize these cross sections. Here are shown a square or rectangular cross section and a T cross section. What we note is that the maximum stresses occur along the middle of the straight side. They do not occur on the sharp outside corners. In this T-beam, we see by far the worst stresses are at these inside or what we call re-entrant corners. So then we talked about the best types of design and the importance of putting a fillet or a round in your cross section. After that, we started to look at what we call long, narrow cross sections. In these long, narrow cross sections, we defined the short side to be 2H and the long side to be 2B. And those are kind of different than what you're probably used to, but that's the nomenclature that's used in our book, so we'll follow it. If we come and look at what the soap film would look like for a long, narrow cross section, we see that for most of the cross section, it's constant. This would be a top view, a side view, and an end view. And we can see that the stresses are the largest right here on the sides, and that they're pretty well constant along the length of the bubble. And we came up with equations then to represent this. Z we let be a parabolic equation where we needed to determine the end coefficient Z0. Doing all of that, we came up with these equations down here for the stresses in a long, narrow rectangle. We were able to determine that J is equal to 16/3 BH cubed, that theta, the angle of twist, turns out to be this expression, and the maximum shear turns out to be this expression here. The one thing I would point out is that to determine J, what we did is we came to this expression right here. Once we had an expression for phi, we came to this expression and performed this integral to get j. And so with our expression for phi, we substituted it into this equation for the torque. We performed this integral. Coming down here, we could see that t was equal to this here, and so we were able to extract from this equation j. And that's how j is determined. It's determined by this equation here, which we derived a few lectures ago. So we're not going to do any more of a review than that, but that is a review for long, narrow rectangles and the equations that are used to compute the stresses, J, and the angle of twist in those. Now, it's really interesting. Many cross sections are built up of several long, narrow cross sections. And so if we have built up structures from those long, narrow cross sections, this is the expression for J that we use. The C in this equation is a correction factor, and it's based on the length to width ratio of all of the beams in the built-up cross-section, or I should say all of the members in the built-up cross-section. And if B over H is greater than or if B is greater than 10H, so if the height of the beam is greater than 10 times the width of the beam, then C's 1. But if you have one or more members where the B to H is not greater than 10, then we let C be equal to 0.91. And that has shown to fit the data, the experimental data, better. The equations that we use to compute the maximum stress are simply this equation here for the stress 2 times the torque times H max over J, where J is given by this expression, and the angle of twist is given by this equation here. It's important to note that H max in this expression is the largest HI, where HI is half the length of the short side of the member. So that's what goes into this equation. Make sure you remember or realize what the H max is. And again, it's noted here. We reviewed this example problem where here in this cross section we have from the outside edge to the outside edge 100 millimeters, and again outside to outside 200 millimeters. And this is in a channel beam. We now go to find the maximum shear stress and the maximum angle of twist. J turns out to be this expression here. Note that C is equal to 1 because all of our members have a greater than 10 length to width ratio. We see for tau max we have 2 times the torque, and then H max is the largest side. So what we have is a 4.5, which is half of this 9 millimeters because it's the largest width that we have, and we take half of that with the H over 2. Theta then turns out to be simply T over G theta, and you can see the answers here. Another thing that's important to note is that B and H go to the center lines of these cross sections. We don't break them into complete rectangles like we did before when we were trying to determine I, but we take the length to the center line of the beam or the cross section and we connect those center lines. And so here we have a length of 97.5 and a length here as shown of 191 instead of the 200 and the 100 that are given in the beam or in the cross section. So we reviewed that. Hopefully that's a good quick review for you. We talked about the difficulty in doing torsional stress with FEA. We'll talk a little bit more about that. We talked about sections that warp and sections that don't warp. And here's a list of several of those sections that do warp. We then just started to talk about torsion of rectangular cross sections that are not necessarily long and narrow. We won't go over the math or the development of this too much, but I certainly want to give you an overview so you see where it comes from. This is still our partial differential equation. This was good for any cross section. And so what we did for the long narrows is we assumed phi was this parabola, and we ended up getting this expression here. And that was essentially the one-dimensional cross section. Now for rectangular cross sections that are not long and narrow, what we essentially do is apply this same equation in two directions. So here we could think of the original direction or one of the directions, and here we use v for the other direction, where v is essentially the same equation, very similar. And so now this becomes our phi, and we're going to substitute this into our compatibility equation and come up with the remaining equations to solve problems. If we make those substitutions, what we end up getting for phi after we do separations of variables is phi is equal to this expression here. And the details of how this is done are given on page 222 of your textbook if you're interested in more detail about this expression. We note that we have 1 raised to an interesting power, we have hyperbolic cosines, and we have an infinite sum that goes on the odd terms. All the other terms in here we are familiar with. The series, it's important to note that this series expression goes to 0 if b over h goes to infinity, which is a long narrow cross section. So if we have a long narrow cross section, this term out here essentially goes to 0. With this expression here for phi, we can write the stresses, which again, sigma zx was the partial of phi with respect to y, as this expression, and sigma zy is negative partial of phi with respect to x, gives us this expression. We then take the square root of the sum of the squares of those two equations to get our tau. We can then determine the expression for j by substituting in phi to this integral for the torque and performing this integral, we end up with j is equal to this expression here, which is again an infinite sum. And this infinite sum is also essentially a function, a very large function of b over h. And when the b over h is very large, this part of the equation essentially drops off and leaves us with what we had before for the long narrow rectangular cross sections. It's been kind of nice that we have had other researchers simplify this expression for j, and what they have done is they have written j is equal to k1 2h cubed over 2b, where k1 then is everything that's left over and is given by this expression. And lookup tables have been made that allow us to compute or look up the value for k1 very quickly. and their lookup values based on the ratio of B over H. These tables, these lookup tables for K1 are given in your textbook. But we kind of build on K1 and introduce another relationship lookup value as well. And that's probably best seen by looking at an example problem. So let's continue to look at this example problem. Here we're considering this beam again, or this cross section. And what we're going to do is to plug the values that we just obtained into the stress equations. Here's sigma zx, and we get this expression here. And for sigma zy, we get this expression here, which turns out to be a 0 and a tau max. And that's what we get by plugging x is equal to plus and minus h and y equals 0 into the expressions for the stresses on the previous page. Hopefully you can see where that comes to be by looking at these integrals and computing some of these numbers. Again, we're going to substitute plus and minus h for x and 0 for y into this expression here for sigma zx, and we'll get 0. And down here, when we do the same thing where we stick in x as h and y is 0, we get tau max. So we end up seeing that tau max is given by this expression here, and we can rewrite tau max as 2g theta hk, where k is given by this expression. So this is k. Little different than the expression for K1 that we just talked about. So what we're going to do now is continue with this, and by combining the previous equation with this expression A that we had for the torque, which had K1 in it, it can be shown that by solving equation A for this theta and substituting it into our tau max expression here, this gives us tau max is this equation. And in this equation we have a K and we have a K1, and they're different. And what we did then is, what some researcher did then is they came and they said, well, let's replace the K and K1 ratio with K2. So K2 is equal to K1 over K. And values for K2 are also given in a table. So as a summary, what we do to compute some of the values here is the torque is J theta, and this is on page 224 of your textbook. J is given by K1 2h cubed 2b, and K1 is the equation given on page 225, and it's also a lookup table. So there's a lookup table for this K1. Then when we want to actually compute the stress, we have the torque over this K2 term, and K2 is another lookup table value that comes from page 226. And we will use these equations for rectangular cross sections, and if the cross section is built up with multiple rectangles, we'll compute J using the above equation for each member and then sum them up, and then use the long narrow equations to compute the stress and the angle of twist. So let's look at an example problem. Here we have a multi-component or a built-up cross section. We'll look at the sections individually and analyze them and then combine them. So it's told us in the problem statement that we transmit a torque T, the shear modulus of the material is G. In terms of T and G, derive formulas for the maximum shear stress and the angle of twist per unit length for each section of the beam. So what we'll come down here and do is note that 2H is always the short side, 2B is always the long side, just as a reminder. we'll take the sum of the rectangular sections 1, 2, and 3, and I've numbered them as 1, 2, and 3. And these are the basic equations that we're going to use to compute those values. And those equations are equation 663 in your textbook. Then if we look at section 1, we have a b over h, which is 4a all over 3a over 8. Solving that turns out to be 10.6. And so from this, we can find that k1 is equal to a third. We essentially have a b over h that's greater than 10, and so we have a long, narrow cross-section. J1 we can then compute as given by this expression here. For section 2, we compute b over h as 5a over this ratio here, which gives us 20, which is greater than 10, and also gives us a k1 as equal to 1/3, and so we can compute J2 as given by this expression. We do the same thing for section 3, and again we get a greater than 10 ratio, and so now we can sum all of these up and get J using this sum, and we'll sum all of these individual terms. J then is given by this equation, and we can come and compute our tau max and our theta. So I hope that gives you an example of how it seems relatively complicated, but it actually turns out to be relatively simple on how to compute the maximum shear and angle of twist in a cross section something like this. As another example, there's example 631 in the textbook. Here we have a steel bar that has a rectangular cross section of 12.7 wide and 38.1 deep, and the bar's subjected to a twisting moment or a torque of 135.7, and the shear yield stress of the material is 82.7. And we're asked to calculate the maximum shear stress in the bar and show in a diagram where it occurs. So to solve this problem, what we will do is we'll use equation 664 for our expression for tau max. So here's our tau max equation. We need to get K2 to do this. To get K2, we compute our B over H ratio. Our B over H ratio turns out to be 3. So from table 6.1, K2 is 0.267. So our tau max becomes this equation here, where we have our B and our H and our K2, and we compute a value of 82.7 MPas. And since tau max is actually equal to the yield stress just reached at the center of the long cross section, or the long side, then we can come and calculate the shear stress in the bar at the center of the short side. And to do this, we're going to interchange the B and the H in the tau max equation, and when we do that, we get tau max is equal to 27.6, which is significantly less than the shear for the long side. So again, I hope this kind of shows how relatively simple these problems can be. Let's look at one more example. This is example problem 6.37, and it shows an I-beam with kind of a unique cross section. The torque is 5,000 Newton meters, and the dimensions of the cross section are as shown. In part A of the problem, we are to determine the maximum shear stress in the cross section. And to do this, we first need to compute the torsional constant for the member. So computing this torsional constant, we'll look at each member individually. For the top flange, we have B over H is 135 over 15, which is 9. This value is less than our magic number of 10, and so we'll go to table 6.1 and pull off K1 is 0.309. Then we can come and compute J for the top flange, and we get this expression here for J for the top flange. For the bottom flange, B over H turns out to be 9.25, so from table 6.1, K1 is 0.31. And so the torsional constant we can compute for the bottom flange is given here. Now for the web, we see that the B over H for the web is greater than 10, and we end up getting our K1 is equal to a third. So for the web, we get this torsional constant. Now we come and sum all of our torsional constants together and get our overall value. Then from equation 663 in the textbook for the maximum stress, we see that we can compute the maximum stress, and we use the long narrow equations for the stress and the twist when we have multiple rectangular elements. And we compute that stress to be this. Now we can determine the angle of twist using our expression for theta as shown here, and we get this result for the angle of twist. So again, you can see how relatively complicated problems can turn out to be fairly simple by using these equations. And the expectation that I have for you guys is that you can use these equations and these lookup values to compute stresses and angles of twist in built-up cross-sections, just like this example problem 637. We now want to look at another type of problem that is very common in the design of industrial components, aircraft, automotive, and other components. And this is where we have hollow, thin-walled torsion members. These can be shafts in torsion that have thin walls to make them light, something like a drive shaft or other shafts that are spinning. A lot of those are symmetric and circular to keep balanced. This little section here that we're going to cover, we'll talk about any thin-walled hollow cross-section independent of it being circular. And it's kind of the same analogy that we used with the soap film. We need to just be careful how we apply it. So again, the theory is based on the membrane analogy, and it's assumed that the shear stress is constant through the thickness. So what we're going to do is we're going to assume that the shear stress through the thickness of the thin wall is constant. And the way this really happens is what we do is we take a bubble and assume that there's a bubble for the outside edge of the cross section. And then we take a flat plate and we set that flat plate on the bubble, and the flat plate has the dimensions of the inside cross section. And so a side view of that is kind of given here, where our bubble would start to go up on the outside dimension and might come up something like this. And then we take a flat plate that has the dimensions of our inside cross section and we smash the bubble. And when we smash that bubble, it comes down, and so the slope between the outside edge and the inside edge is usually really thin, and we assume that it's a constant through that section. And in doing so, that tells us that there's no change in that slope throughout the cross section. The shear stress around the boundary is not constant unless the thickness is constant. So if our cross section here changes, if our wall section changes, then our slope will change and our stress will change. But if our cross section is the same thickness and constant all the way around, our slope will not change and we will have a constant stress or a uniform stress. These equations are good as long as the wall thickness is relatively small compared to the overall cross-section. And the rule of thumb is given here. The expressions in this section are good when the wall thickness is less than 10% of the minimum cross-section dimension. So our minimum cross-section dimension might be something through here, looks like to me. And as long as our wall thickness is less than 10% of this distance here, then these equations that we're talking about are valid. So to just quickly review the derivation of these a little bit, we recall from textbook equations 652 and 53 that z is given as this and p over s is given as this, and we can make these substitutions into our expression for tau. And then we can write tau as 1 over c tan alpha, and for small angles, we can let this be 1 over c sine alpha. And this quantity introduces a new term, and this term is Q, and Q is called the shear flow, and it's tau T, where T is the thickness, tau's the stress, and then we have the shear flow Q. And we're going to build on this idea of shear flow because it's easy to visualize for us. Sometimes it can be hard to visualize the stress and the angle of twist, but this Q is a little bit easier to visualize in some situations. So Q is equal to tau T, and it's called the shear flow. So the shear flow is constant around the cross-section of the member. It's also equal to the stress function phi. And we note that the stress is only constant around the thickness of the hollow member if the thickness is constant. But the shear flow is not. The maximum shear stress would occur at the minimum thickness. So we recall that phi is proportional to z. We make that substitution. We come up with our expression for t. We go through all these integrals, and we end up getting that tau is equal to t over 2at. So the shear stress tau is equal to the torque over 2 times the area times the thickness. And this area in this equation for the shear stress is the area enclosed by the mean perimeter of the cross section. And so what we need to do is we need to find the perimeter of the outside edge, the perimeter of the inside edge of the hollow member, and then take the average of those. And that seems kind of complicated, but it's actually fairly straightforward. So once we do that, we can get tau theta g and the dimensions of the cross section, and they're all related in an expression that can be derived by summing the forces in the x direction as shown below. So here we're going to sum the forces, and we end up getting this expression here. And this integral with the circle in it implies that we integrate around the perimeter or around the area. And in this expression, L is the length of the perimeter of the cross section. And we can express theta as this expression, and then often the thickness is constant. And if the thickness is constant, we can write this integral of dl over t as just the entire length divided by the thickness. And we can pull out all of these constants here because Q is constant. Q is not a function of thickness and stuff. So Q is a constant. It is a function of thickness, but it's constant around the cross section. It doesn't change, so we can pull it out of the integral. So writing tau as Q over T lets us write this expression here, and this integral is simply the length divided by the thickness. So it reduces this expression significantly in complexity. So there are cross sections where the thickness might change. And so what we do is this integral simply becomes the individual sums of the lengths divided by their particular thickness. And so if we had a cross section that had 3 different thicknesses to it, would add up the ratio of L1 to thickness 1 plus L2 to thickness 2 plus L3 to thickness 3 and so forth. Theta can then be expressed as this. The torque is J theta, where J is this expression. Again, we've got our A up here and we've got our integral. And we can come down here and write this as the torque is given by this expression here. And then finally we can express the theta as this expression as given by here. And we'll look at how to use these expressions here in just a minute. We're now going to look at using multiple components. And if a cross-section has multiple compartments that are thin-walled, and these occur frequently. Here's several examples of multiple compartments in large bridges where the truss structure has been built, and we would be looking at the torsional stress in a bridge. Here's an overhead ramp, a road ramp, and here is an airfoil of an aircraft. So these multiple component thin-walled sections occur in many types of civil engineering and mechanical engineering parts, and it's an important problem for us to understand. Here's another example of an airfoil with multiple compartments in it. This would be like the wing of an aircraft. To use these expressions and develop these equations, what we do is we look at summing up the individual compartments that we just previously talked about. So in this expression here, we see that the torque is equal to a sum of the individual AIs and QIs, where AI is the area bounded by the mean parameter of the ith compartment, and QI is the shear flow in that ith compartment. And then we can come and get theta by computing this expression here. And the only thing that we got to be careful with is the Q prime. And the Q prime is the shear flow for the compartment that is adjacent to the ith compartment. And so we would be looking at the shear flow in one compartment here, and this Q prime would be the shear flow in the adjacent compartment. And the thing that's important to note is that Q prime is equal to 0 if we're looking at a boundary compartment or an outer boundary, because there is no adjacent compartment. And so we'll go through an example and show you how that makes a little bit more sense. The maximum shear stress occurs where the membrane has the greatest slope, or where this quantity Qi minus Qi prime, or Q prime, is the maximum for the nth compartments. So let's look at an example. Here we have a cross section. It's one compartment, but it's made up of several different little regions. The torque is 3 kilonewton meters, and we are asked to determine the maximum shear stress in the member and the angle of twist. So we know our basic equations are given by tau is this expression here, theta is given by this expression here, and we need to find the terms in these expressions to solve for these quantities. The area enclosed by the mean perimeter A is given by 0.14 times 0.08 times this quantity here. And if we look at that to make sure we understand where that comes from, what we have is we have the 0.14 is this center to center distance. Note that in the problem statement, the center to center distances are given and the outside edge distances are not given. And so that's kind of handy because we can use this automatically without having to take the outside minus the inside. So this would be like the area of an outside rectangle, and then we come over here and we subtract off the circular part. And again, we can see that this center line dimension is 60 millimeters, and the thickness here is 4. And so this area of a circle is given by this, and we take half of that because we're looking at a half a circle, and that's what is subtracted. So our area is given by this expression here. Then we can come over and can compute tau max. Note that tau max is obtained when we have the smallest t. And so back up in the picture, we look where we have the smallest t. Out here, this is all 5 millimeter thick material. This is 4 millimeter thick material. And so our largest t will occur with the 4 millimeter thick material, and tau max is given by this. Now we can compute the shear flow, and the shear flow is given in compartments. So Q1 is tau max times T1, and so we can get this expression here. And now we have multiple lengths because we have multiple thicknesses. So our L1 is just going to be pi d over 2, half the circumference of this circle, and we know that the d is 60, and so we can compute the length of that. And then L2 is the length of all the rectangular components. We have one at 140, and then 2 at 80, and then another one here at 80. And so that total length of the 5 mil thickness is this. And so now we can do this integral here and look at our compartments. So when we come to do this, we're going to look at the two individual compartments. So we'll essentially do this integral by summing two components. So for the first one, we'd have Q1 minus Q prime, and since the Q1 is an outside boundary, there's no internal boundary there. Q prime goes to 0. Same thing for 2. We have Q2, it's an external boundary, it goes to 0. And this integral of Q minus Q prime reduces to this expression here, and we can get a value of 15. Then we can come down here and plug in and compute our theta and get our angle of twist. So this problem was kind of straightforward because we didn't have compartments that were related with an internal boundary. We had kind of one single compartment, and so our Q primes go to 0, which make this relatively straightforward. We'll now look at an example where we have individual compartments. So in this example here, we want to do kind of the same thing. And again, you can see that the dimensions that are given are the mean perimeter dimensions. We have one big cross section here and then two smaller compartments here. And what we're asked to do is come down and determine the angle of twist in this problem. And so we're going to apply the torque and then draw the torques in each compartment. And we're going to note that all the torques need to go the same way. So up here in this compartment, Q1 is going in this counterclockwise direction. So Q2 has to go in that counterclockwise direction, and Q3 has to go in that counterclockwise direction. You can't change the direction on these Q's. They all go the same way, and that will become very important for us. We note that A1 is simply H over 2, B over 2, and so we get this expression. We note that A2 and A1 are equal, and then A3 is simply 2 times A2 or 2 times A1. The angle of twist in each compartment must be the same because they are connected to each other. And so we know that theta 1, 2, and 3 have to all be equal. we can express theta 1 as the general equation is given by this expression right here. And now if I go look at this individual compartment, what I'm going to have is I'm going to have Q1, and it's going to be times by H over 2 plus B over 2. And that comes from these dimensions up here of H over 2 and B over 2 for this side, these two sides here. Now I have a Q1 minus Q2, which would be this side. And the reason why this is minus is because Q1's coming around counterclockwise, but on this edge here, Q2 would be going around clockwise on this edge. And so the two subtract over the length of B over 2. And the same thing occurs here with Q1 and Q3. Q1 would be coming up on this wall. Q3 would be coming down on this wall. And so we would have a Q1 minus Q3 times the distance H over 2. And so that becomes my theta 1. Hopefully you can see how theta 2 and theta 3 are very similar for their individual components, or their outside compartments, I should say. The dimensions just add, and then on the inside, these Q's subtract over the boundary. And so now we know that theta 1 has to equal theta 2. We can set those two equal to each other, and we can get this expression here, and this expression can only be true as long as Q1 equals Q2. And so we know Q1 equals Q2, and now we can look at theta 1 and theta 3, and setting them equal to each other, we get this expression, and we can come down and show that in order for this to be true, Q1 has to equal Q3. And so we can show that Q1, Q2, and Q3 are all equal in this problem, and that's what we were asked to do in the problem statement. So hopefully this example shows you how to use the Q and the Q prime. Thanks for watching this video. Hope you have a great day.